B, now we want to find E for R greater than R. Okay, so we want to approach this in a very similar way. We're not going to have a whole lot of space. I think I can scroll down a little bit and give myself some more space. Oh, okay. Yeah, but I don't know if I want to scroll down yet. Oh, there we go. Okay. So for the second part of this, now I'm looking for what the electric field is outside of this sphere. So again, we can ask ourselves, do we want to use Gauss's law or Coulomb's law? Gauss's law or Coulomb's law would make us cut this up into many little tiny pieces of charge, each of which would have a different distance out to this location here, I guess, which is some place that E is greater than R, or sorry, radius lowercase r is greater than r. So that would be a lot of work. The other option would be Gauss's law and just draw a new Gaussian surface, like a bigger sphere, and see what happens. So I think that's what we'll try. So our new Gaussian surface will be a bigger sphere. Can Gaussian surfaces go through words and graphs? You betcha. Look at it. Phew, that's pretty cool. Okay, so I just drew a larger sphere. So this is my Gaussian surface for part B. Okay. So with that Gaussian surface drawn, I'm pretending that it's like a constant radius Gaussian surface, even though it's not drawn very well. So let's try part B. So I scroll my way down here a little bit. For part B, Gauss's law would say the net flux equals the integral of E dotted with dA, which equals the charge enclosed over my dielectric, whatever material I'm passing through space. Yeah, whatever material fills that space. That's kind of what I'm saying. This is where we're going to run into a slightly challenging situation. Yeah, inside versus outside. Because we'd have two different... Oh no, this actually isn't going to run into a problem at all. Well, only a slight problem. Out here, I am treating this as though this is a vacuum, so this really will be E0 there. Sorry, we were just thinking that through out loud as we were talking about it in class. But, yep, outside the Gaussian, or outside the charged object, I have free space.
So are we almost ignoring the vector as it travels through the sphere, and we're only picking it up on the outside?
Okay, so as I look at that, my Gaussian surface does meet all three criteria, where E is going to be the same strength at all points around there. E is always going to be parallel to dA, and the dA is easy to calculate. So we can kind of jump from this step straight to E times the area. 4 times pi times radius squared is the area of my new big Gaussian surface. And that's equal to the charge enclosed over E0. Right? How much charge is enclosed? All of it. So plus Q is in there. So this is going to take significantly less work because the electric field just equals plus Q over 4 pi E0 R squared, which, if we like it written with Coulomb's constant, is the same thing as KQ over R squared. Okay, so this says that the electric field, due to this distribution of charge, is just going to be like a point charge acting at the center. So if I'm looking at the graph of this, it's, with the exception of the difference in dielectric, this graph is going to be more or less something like this going downward, because it's a 1 over R squared graph beyond there. Okay, so something to that general effect is what this graph's going to look like. Okay, and so that kind of takes care of parts B and C. The second video was much shorter than the first.